This is objective 1, where we are using pulse width modulation to control the intensity of an LED's brightness. So what we're doing here is we are using pin 11, which is a PWM, or pulse width modulation digital output pin. So what this is doing is it's sending the power in a wave form, up and up and up and up and up and down. And this comes out to be various voltage. And what I'm doing here is using a for loop to gradually, every time it goes through the loop, lower the voltage, or lower the pulse width modulation by 1 unit, and then therefore bringing it from 100% power down to 0, and then starting over again, and just doing this over and over and over again forever. This is the code for objective 1, where we are turning the LED on and off in a variable manner using pulse width modulation. Here we start with the setup, where we declare the pin 11, which is what the LED was plugged into, as an output. That's the only thing we need in setup. Then we go to the loop, where I used a for loop to gradually bring the value of the LED down from the high of 255, which is the high end of pulse width modulation, down to 0, subtracting one increment each time it goes through the loop, and doing this over and over and over again until it reaches below 0 or equal to 0, which then it starts over at 255 and goes on forever, which will cause the LED to start at a very bright intensity and slowly come down to being off, and then going back to the bright intensity, gradually coming down. This is objective number 2, where we are using a potentiometer to control the speed of a motor, using the potentiometer to control the voltage output coming from the Arduino to the motor. So the way this works is the power and ground are supplied by the Arduino to the power bus, which the motor and the potentiometer are both connected to. The potentiometer is then sending the signal wire through this yellow wire to analog pin 0, giving an analog input to the Arduino, which then divides by 4 to get a PWM output value to pump into output pin 9 as an analog output using pulse width modulation, which then goes to the motor, positive side of the motor, and depending on the pulse width modulation value will depend on what voltage the motor gets. This then goes through the motor and then back to ground bus, where the motor is plugged into. And as you can see here, with this direct wire, I can slowly turn the motor down all the way until it stalls. This is objective number 3. It is a similar circuit. The code is actually exactly the same as was in objective number 2, except now we have a transistor integrated to better control the speed of the motor using the potentiometer. Now right now there is actually current going from the Arduino and power supply to the motor, but it's not enough to get it moving, so right now it's stalled. But if we turn this up using the potentiometer, it starts right up, and we can turn it all the way up to the maximum speed. But then now that it's moving, there isn't that stall current needed to get it going. So when we turn this back down all the way, the smallest amount of current that we can supply when the potentiometer is at its minimum is not is enough to keep the motor spinning and it doesn't stall out. Now the wiring diagram set up on this is power and ground coming from the board to the bus. This is mainly to supply the potentiometer power, but it's also to bring the ground for the transistor back into the same loop as the potentiometer and Arduino logic board. The motor and transistor are getting their main power from an external power supply, in this case a 9-volt battery. The power comes in through the power bus, then powers the switch. There's a signal wire coming from the potentiometer going to analog pin 0. This then does the logic using the programming on the board, comes out through an analog right pin 9 using pulse width modulation to have an analog signal, which then goes into the transistor and is transmitted out to the motor as various voltage values. This is the code for Objective 3, where we used the value of a potentiometer in order to variably control a motor using pulse width modulation. So we start by declaring our global variables, the potentiometer value equal to 0, and the initial PWM value is also equal to 0. The setup, we're declaring pin mode 9 as an output, which is the pin going to the motor. Then we go to loop, where we have a delay in there just to give it an ability to read over and over again in a timely fashion. We then read the analog pin and give the potentiometer value a real value, or a new value, based on what the potentiometer is reading from the analog input. This is then put into, then here we are using declaring the PWM output value as a scale of the potentiometer value, which is in scale of 0 to 1023, and what this does is it changes this scale of 1023 into an evenly scaled from 0 to 255, converting this from the analog input to a pulse width modulation analog output, which have bigger increments, which means you have a smaller count. So what this does is it takes the potentiometer value into this. It's at a value of 1023. It does some math in the background and spits it out as a value between 0 and 255, which is then written to the motor pin in order to tell the motor how to spin at what speed. This is objective number 4, where we have the push button and the potentiometer being used in a AND boolean to turn the motor on or off. Right now it's in the state of off because the potentiometer is, even though the potentiometer may be above 500, the button is not pressed, so the AND statement is not true. Therefore the motor is off. In the case where we have the potentiometer turned all the way up and push the button, we give the motor a little kick. Turn the potentiometer all the way up, push the button, and give the motor a little bit of a kick, and it comes on. Now we have to give the motor a little bit of a kick because the current coming through the Arduino is not enough to get past the stall current to get the motor initially moving. Unfortunately, I don't have my battery with me right now, otherwise I would be able to run that without giving it a kick to start it. So as you can see, I can let go of the button, that turns it off, push the button, and start the motor again. If we keep the button pushed and turn the potentiometer down instead, it also acts as an off switch for the motor. The wiring setup for this is the same as usual, or the same as the past two objectives initially, using the potentiometer, power and ground to the potentiometer from the bus, signal wire going to analog pin 0. This is then used in the code as an analog value, and read to be a number between 0 and 1023 based on the input voltage. When this number is above 500, the motor turns on, or at least half of the AND statement is true, and the motor has the possibility of turning on. The other half of the AND statement is that this button must be true, and when both of these are on, or the button is true, and the potentiometer is above a value of 500, the motor spins at full power, because I have it set to be a digital write for the motor at high when both of these statements are true, since the speed of the motor doesn't currently matter to us. This is the code for objective 4. We start by initializing the global variable, which is the bumper switch pin, which I have plugged into pin 8. We then declare pin 9 as an output, which is where the motor is, and then pin 8 as an input pull-up, because it's a push button and we don't want any bounce errors. Since this is a pull-up though, later in the code we'll have to use the bump value as equal to 0 or low in order to notice when it's pressed, because when it's not pressed the input is always being pulled up to 5 volts. When it's connected it goes to low instead of high. We then move on to the loop, where we initialize our local variables of the potentiometer value and the bumper switch value. Potentiometer value is going to be analog, the bumper switch is going to be digital, because it's either just on or off, whereas the potentiometer is a variable resistor from anywhere from 0 to 1023, or in our case 0 to 5 volts in a scale of 0 to 1023. We then read those two values. Potentiometer is into analog 0, and the bumper switch value is coming from the bumper switch pin declared at the top. And as I stated here, since we are using the pull-up, the bumper switch value, in order to say something is true when it is pressed, needs to be equal to low or 0, because the pull-up is always keeping it at high when the circuit is open. And this is in an if statement, Boolean ANDed with a potentiometer value greater than 500. So what this is saying is that when the bumper switch is pushed and the potentiometer value is above 500, do whatever's inside. So if the bumper switch wasn't pushed but the potentiometer is above 500, it's not going to execute it, vice versa. So in this case, I had the bumper switch pressed, the potentiometer is above 500. It will run what's in this if loop, if statement, and in this if statement I have the motor turning on using pin 9 with digital write, because we don't care what the speed is, so it just needs to be on or off. Digital write 9 high, the motor turns on. When this statement is no longer true, it kicks out, goes to the else. Else means anything else is happening, that's what does. So the else executes whenever this is not true, and it turns the motor off.